In the unforgiving physics of aerial combat, there are no metaphors. Every bolt is a potential point of failure, every panel a compromise between stealth and strength, and every innovation a wager on the future of warfare. An aircraft is the physical embodiment of a nation's strategic doctrine, a declaration of intent written in carbon fiber and titanium alloy. Within this context, the Chengdu J-20A Mighty Dragon is far more than a new fighter jet for the People's Liberation Army Air Force, PLAAF. It is the culmination of a multi-decade national project to achieve parity in a technological domain once exclusively held by global superpowers. Its sleek, menacing form patrolling the skies over the East and South China Seas represents the materialization of a fundamental shift in the global balance of power, a machine whose very existence has forced a recalculation of military strategy in Western capitals and accelerated the race toward the next generation of air dominance. As China's first indigenously developed and mass-produced fifth-generation combat aircraft, the J-20 signifies the moment the PLAAF transitioned from a client of foreign technology to a peer-level competitor, making China only the second nation to field an operational stealth fighter fleet and fundamentally altering the strategic landscape of the Indo-Pacific. The forging of this dragon was a process defined by a doctrine of iterative urgency, a stark contrast to the West's more deliberate and often protracted development cycles. The J-20's lineage traces back to the ambitious JXX program of the late 1990s, an initiative to leapfrog generations of aircraft design. Chengdu Aircraft Industry Group's proposal, known as Project 718, was selected over a competing design from Shenyang, setting in motion a remarkably rapid evolution from concept to combat readiness. The first prototype, numbered 2001, took its maiden flight on January 11, 2011, stunning international observers with its advanced configuration. What followed was not a decade of secretive refinement, but a visible, almost audacious series of improvements played out across a succession of prototypes. Prototype 2002 appeared in 2012, followed by 2011 in 2014, which introduced a new stealth coating, redesigned vertical stabilizers, and an electro-optical targeting system. Later airframes, 2016 and 2017, showcased further refinements to the diverterless supersonic inlet, DSI bumps, and a reshaped cockpit canopy for improved pilot visibility. This approach suggests a philosophy more akin to agile software development than traditional aerospace engineering. Build a viable product, field it, learn from it, and rapidly iterate. It reflects a strategic acceptance of a good-enough-for-now platform to close the immediate capability gap while simultaneously pursuing the technology for a better platform later. This stands in contrast to the Western model of aiming for a near-perfect final product from the outset, a process that can take decades. The most significant challenge and the program's long-standing Achilles heel was propulsion. Early production blocks of the J-20 were a compromise, powered by Russian-supplied Saturn AL-31F or 117S engines, capable but not optimized for the airframe, and a clear dependency China was eager to shed. The next step was an interim domestic solution, the Shenyang WS-10C, which improved reliability and performance, but still fell short of the platform's ultimate design goals. The true culmination of the program arrived with the designation J-20A, the variant defined by the integration of the indigenous CN WS-15 high-thrust turbofan engine. This engine is not merely an upgrade, it is the enabling technology that unlocks the airframe's full kinematic potential. The J-20A also features subtle but significant airframe modifications, including a reprofiled nose cone and a deeper, more pronounced spine running the length of the fuselage, likely to accommodate additional fuel, upgraded avionics, and the critical power and thermal management systems required by its advanced sensors. The J-20A, therefore, represents the program's maturation, the point at which a highly advanced airframe was finally paired with an engine capable of exploiting its design. The anatomy of this predator is a study in deliberate compromise, balancing the competing demands of stealth, speed, and agility. It is a large and heavy fighter with a length of approximately 21.2 meters, a wingspan of 13.1 meters, and a maximum takeoff weight tipping the scales at a formidable 37,000 kilos. Its defining aerodynamic feature is a canard delta wing configuration comprising large, all-moving canard foreplanes paired with a classic delta wing and outward-canted, all-moving twin tails. This layout is inherently unstable, a desirable trait in a modern fighter as it confers exceptional maneuverability, managed by a sophisticated fly-by-wire system. The close-coupled canards generate powerful vortices that flow over the main wing, enhancing lift and allowing for superior turn performance at both transonic and supersonic speeds, and granting the pilot sustained pitch authority at high angles of attack where a conventional tailplane would stall. However, this kinematic excellence comes at a price. Aircraft design is a zero-sum game, and the choice of canards presents a significant challenge to achieving all-aspect stealth. The moving surfaces and the unavoidable gaps between the canards and the fuselage create sharp angles and edges that are notoriously difficult to shield from radar waves, particularly from frontal and oblique aspects. Chinese researchers have undoubtedly invested heavily in mitigating these effects through specialized coatings and precise shaping, but the fundamental trade-off remains. This design choice is a powerful indicator of the J-20A's intended role. Rather than a deep penetration asset designed for sneaking through dense, multi-layered air defenses where all aspect stealth is paramount, the J-20A's configuration points toward a role as a high-speed, long-range interceptor where frontal aspect stealth combined with superior kinematic performance is the priority. To achieve this low observable signature, its construction relies heavily on advanced composite materials to reduce weight and radar cross-section, RCS, supplemented by meticulously applied radar-absorbent materials, RAM, and low observable coatings. The overall shape incorporates key stealth features, including a chiseled nose section and a blended wing-body fuselage that minimizes right angles, diverterless supersonic inlets that shield the highly reflective engine compressor blades from radar, and 3 internal weapons bays to maintain a clean, radar-defeating profile during combat patrols. Beneath its stealthy skin lies the ghost in the machine, a technological core of immense power and sophistication. The J-20A's defining feature is its pair of WS-15 engines, each generating an estimated 40,000 pounds of thrust with afterburner. This raw power finally endows the aircraft with the critical 5th-generation capability of supercruise, the ability to sustain supersonic flight, potentially approaching Mach 2, without the use of fuel-guzzling afterburners. This allows the J-20A to close distances rapidly, expand its engagement envelope, and dictate the terms of an intercept. This propulsion system feeds a suite of advanced avionics that represents the true center of gravity in modern air combat. Housed within the large, chiseled radome is a powerful active electronically scanned array, AESA, radar, believed to contain between 2,000 and 2,200 transmit-receive modules, giving it a significant aperture for long-range detection and tracking. Recent breakthroughs in domestic semiconductor technology, specifically the production of high-purity silicon carbide, SiC substrates, have reportedly tripled the efficiency and effective range of these radar systems, a claim that, if true, represents a significant leap in sensor capability. Complementing this active sensor is a suite of passive systems designed for silent hunting. A chin-mounted faceted pod houses an electro-optical targeting system, EOTS, which functions as an advanced infrared search and track, IRST, sensor, allowing the J-20A to detect and track the heat signatures of enemy aircraft without emitting any radar signals of its own. Furthermore, the airframe is embedded with a distributed aperture system, DAS, a network of 6 smaller electro-optical sensors that provide the pilot with a complete 360-degree spherical infrared view of the surrounding battle space, enabling unparalleled situational awareness and missile launch detection. However, possessing these sensors is only half the battle. The true measure of a 5th-generation fighter is its ability to perform sensor fusion, using immense computational power to integrate the disparate data streams from the AESA radar, EOTS, DAS, and offboard data links into a single, coherent, and intuitive tactical picture for the pilot. The praise from a senior U.S. Air Force general in 2022 regarding a professional encounter with J-20s, specifically highlighting being impressed with the command and control, suggests that China's fusion engine is mature and effective. This software-driven capability is so critical that China, mirroring the U.S. development process for the F-22, utilized a modified Tu-204 airliner as a dedicated flying testbed to integrate and debug the complex avionics suite long before the fighter itself was ready. This level of investment underscores a deep understanding that the aircraft's lethality is determined less by its physical performance and more by its ability to process information. This immense processing power generates a significant engineering constraint: heat. The J-20A's noticeably deeper dorsal spine is not just for aesthetics. It provides the necessary volume for an uprated power and thermal management system, a sophisticated cooling architecture essential for preventing the aircraft's powerful electronics from overheating and throttling their own performance. The J-20A is as much a flying supercomputer as it is an airplane, and its revised shape is the physical evidence of a mature, systems-level solution to keeping that computer cool under pressure. The ultimate purpose of this complex machine is to deliver its talons and teeth to the enemy. The J-20A's primary armament is carried internally to preserve its stealth characteristics. The main ventral weapons bay is configured to carry 4, and with the advent of new folding fin missiles, potentially 6, PL-15 very long-range air-to-air missiles. The PL-15, with a NATO reporting name of CHAA-10 Abaddon, is a weapon that defines the J-20A's mission. It is a formidable missile with an estimated operational range exceeding 200 kilometers, powered by a dual-pulse rocket motor that allows it to conserve energy during its mid-course flight and reignite for a high-energy terminal attack phase, making it exceptionally difficult to evade at long distances. Its guidance is provided by a miniature AESA radar seeker, offering superior tracking and resistance to electronic countermeasures. For within visual range engagements, 2 side bays located behind the engine inlets each house a single PL-10 short-range missile. The PL-10 is a highly agile imaging infrared-guided weapon with thrust vectoring control, capable of high off-bore sight shots cued by the pilot's helmet-mounted display. Notably, the J-20 lacks an internal cannon, a deliberate design choice that underscores its doctrinal focus on beyond visual range combat. For missions where stealth is not the primary concern, the J-20A can be configured in beast mode, utilizing 4 underwing hardpoints to carry a massive external payload. This can increase its total missile count to as many as 18, with a total ordnance weight approaching 28,000 pounds, sacrificing its low observable profile for overwhelming firepower. This operational flexibility allows the J-20A to serve as a key asset within the PLAAF's broader anti-access area denial (A2AD) strategy. Its combination of stealth, supercruise speed, and the extreme range of the PL-15 missile makes it an ideal platform for a very specific mission: hunting and destroying an adversary's high-value airborne assets. Modern expeditionary air power, particularly that of the United States, is critically dependent on a network of large, vulnerable support aircraft like KC-135 tankers, E-3 Sentry AWACS, and various intelligence, surveillance, and reconnaissance ISR platforms. By penetrating the outer defensive screens, the J-20A is designed to target these crucial enablers, effectively severing the logistical and command and control lifelines of an opposing force. In this sense, the J-20A is an anti-air power asset, engineered not just to fight other fighters, but to dismantle the entire system that makes them effective. Placing the Mighty Dragon in its global context reveals that it is not a direct copy of any single Western design, but rather a unique answer to a specific strategic question. A direct comparison with its fifth-generation counterparts is less a matter of determining who wins, and more an analysis of differing design philosophies shaped by geography, doctrine, and national ambition. Against the Lockheed Martin F-22 Raptor, the benchmark for air dominance that the J-20 was designed to counter, the Chinese aircraft trades some of the Raptor's supreme agility and all-aspect stealth for significantly greater operational range and a higher top speed. The F-22 was built to achieve absolute air superiority anywhere in the world. The J-20 was built to deny that superiority within a specific theater of operations. The contrast with the Lockheed Martin F-35 Lightning Saku is even more stark. The F-35 is a networked, multi-role quarterback of the skies, a versatile but kinematically less potent aircraft whose primary strength lies in its unparalleled sensor fusion and data-sharing capabilities, designed to serve multiple branches of the military and numerous allied nations. If the F-35 is a stealthy flying sensor node, a scalpel, the J-20A is a long-range interceptor, a spear. Its design is specialized for air superiority and strike interdiction, not the jack-of-all-trades mission set of the F-35. Finally, when compared to Russia's Sukhoi Su-57 Felon, the J-20's success is highlighted by its execution. While the Su-57 may possess impressive supermaneuverability, its development has been plagued by production delays, and its stealth characteristics are widely considered to be compromised with an RCS potentially orders of magnitude larger than its American and Chinese counterparts. The PLAAF, meanwhile, is mass-producing the J-20, fielding a credible and numerous stealth fleet, while Russia struggles to build more than a handful of operational Su-57s. The difference is not just in the aircraft, but in the industrial and technological capacity to realize them at scale. The J-20A is not a failed F-22 clone or a less versatile F-35. It is a successful and purpose-built solution to China's unique strategic problem: how to counter and hold at risk the expeditionary air power of a peer competitor from a position of regional defense. The Dragon's shadow is long, and its future evolution is already taking shape, pointing toward the next era of air combat. The most significant development is the two-seat J-20 variant, which is now entering operational service. 1. This is not a simple conversion trainer. The second crew member is a dedicated mission manager or weapon systems operator, tasked with handling the immense cognitive load of complex missions, including electronic warfare and, most critically, the command and control of unmanned loyal wingman drones. 2. This development positions the J-20 platform as a crucial bridge to sixth-generation air combat, where manned aircraft act as command hubs for swarms of autonomous or semi-autonomous systems. 3. The J-20S is the PLAAF's practical solution to the human-machine interface challenge of managing a distributed, networked combat system. This evolution is backed by a massive and accelerating industrial base. With over 300 J-20s already produced and production rates reportedly exceeding 100 units annually, China is on track to operate the world's largest fleet of stealth fighters, a strategic advantage in itself that can offset a qualitative edge through sheer mass. 4. The J-20A, therefore, must be seen not as an endpoint, but as a catalyst. It is a machine that has successfully dragged the PLAAF into the 5th generation, forced a global reevaluation of air power, and is now evolving from a lone predator into the central node of a collaborative and partially unmanned aerial combat ecosystem. It has cast a long shadow over the future of air power, ensuring that the skies of the 21st century will be a far more contested domain.